All right. So in this video, we are going to be going through the two proofs of Theorem 5-10 and Theorem 5-11. So let's talk about the geometric proof of Theorem 510, which again says a line that contains the midpoint of one side of a triangle and is parallel to the other side passes through the midpoint of the third side, right? So let's talk about how we would prove this. Within these proofs, I'm going to be doing them pretty informally, so the notation isn't going to be fully proper, but it's going to be proper enough that way you can easily follow along. And throughout it, if you want to pause and try out from that point and then resume to check your work and then see if things match up, by all means, go for that. I feel that's going to be a really great strategy. So for this proof, we want to prove that the point of intersection from the median of the triangle is going to actually be the midpoint. So the first thing that we're going to do is we're going to construct an auxiliary line that's going to be parallel to the base. All right, so we know that this is also going to be parallel. So we have three parallel lines. Well, we also know that M is the midpoint, then we have two congruent pieces. So from that new auxiliary line going down to the base of the triangle, we're going to have two congruent pieces because M is the midpoint. From here, using theorem 5-9, the previous theorem, we now know that these other two pieces have to be congruent to each other, because if we have three parallel lines and we have a transversal going through that creates congruent parts, then we know that any other transversal going through those same lines have to create congruent pieces. From here, we have a line that contains the midpoint of one side and that has to contain the midpoint of the other side. So this question mark has to be the midpoint of the right-hand side of the triangle, right? And that was pretty informal, but hopefully it was enough that way we could understand it. And that one's a bit simpler than the next theorem. So theorem 511, again, we don't refer to them as 511, 59, 510, but just for the aspect of time, I'm just going to be referring to them as it. So we have two pieces of information that we are given in this theorem. The segment that joins the midpoints of two sides of a triangle is one, parallel to the third side, and two, it's half as long as the third side. So let's talk about the geometric proof of these pieces here. So if we are talking about, we have a triangle. Let's say we have triangle ABC, and of that there is a segment that connects the midpoints, right? So let's say D is the midpoint of AB and E is the midpoint of AC. We would know that we have AD is congruent to DB and AE is congruent to EC, right? Those are some givens because we know that D is the midpoint of AB and E is the midpoint of AC. So here's where it gets fun. We're going to draw an auxiliary line from C called CX that's going to be parallel to AB. So we know that AB is parallel to CX, right? So we are stating that we can draw these lines, right? We can draw an auxiliary line. From here, we're going to draw an auxiliary line from DE or point E that intersects that new line at a point, and we're going to call that point F. So all we did was just draw two auxiliary lines so far. Again, if you want to pause here and try it out, go for it, and then resume when you're ready to see what happens. So we know that DEA, the angle DEA, is going to be congruent to the angle CEF because those are vertical angles. We're going to know that angle BAC, let me do that in blue, BAC is congruent to XCA because those are alternate interior angles. We have line AB and line XC, those are parallel. So the line AC cuts through as a transversal. So we have those alternate interior angles. As you can already tell, AE is congruent to CE because we know that E is the midpoint of that entire segment AC. So now we have triangle ADE is congruent to triangle CFE using angle side angle. From here, we can use corresponding parts of congruent triangles. So DE has to be congruent to FE or EF, and we know that AD is congruent to CF. So notice how I'm using the same marking on AD as I am for CF because those are corresponding parts. If you look at it, BD, segment BD, let me highlight for you. Segment BD is parallel and congruent to FC or CF. Since I have congruent pairs of opposite sides that are also parallel, that means we have a parallelogram here. We now have a parallelogram. And if you look at the parallelogram, we might be able to notice some things. We're going to know that DE has to be half of BC because DE is half of DF, and we know that DF is congruent to BC. So DE has to be half of BC, which is where we get this theorem, right? But you may want to know how to do it algebraically. Now, please bear with me. It's going to get sloppy. I'm going to do my best here to try to make it as simple as possible, but please understand that it is going to get messy. So if at any point you're like, whoa, I don't know what's going on, that's totally okay. But hopefully I'm going to do it in a way that you're going to be able to follow. So let's talk about the first aspect of this theorem. We want to prove that segment DE in this diagram is going to be parallel to BC. Well, we know to be parallel, they have to have the same slope. So we have to start to label some points here. So what I'm going to do is I'm going to label point A, x1, y1. I'm just going to have some arbitrary points here. B is going to be x2, y2. And C is going to be x3, y3. So if I want to find the points of D and E, well, I know it's the midpoint, so I can use the midpoint theorem. So D is technically going to be x1, x2 over 2, comma, y1, y2 over 2. And likewise, we can do the same thing for E. We're going to get x1 plus x3 over 2, y1 plus y3 over 2. All right, so those are our coordinate points, and we got that because we know they are the midpoint. So if we want to calculate the slope, well, let's calculate the slope of BC because that's probably going to be easier. So the slope of BC would be y sub 3 minus y sub 2 over x sub 3 minus x sub 2, right? And we don't have any more information right now. So we know that the slope of BC is going to be here. So now let's talk about finding the slope of DE, which is where it's going to get fun. As you can see, we have some fractions here. So we have to figure out the difference of our y's over the difference of our x's. Well, E has the y1 plus y2 over 2 minus y1 plus y2 over 2. Oops, I just realized I made a tiny error here. This should be y sub 3. My apologies. And now that's going to be over the x value. So x1 plus x3 over 2 minus x1 plus x2 over 2. If we multiply the numerator and the denominator by 2, if we increase everything by a factor of 2, you are going to see that we now have no more fractions within the fraction. So it really turns into now y1 plus y2, y3, sorry, minus y1 plus y2 over x1 plus x sub 3 minus x1 plus x sub 2. Well, you might see something here. In the numerator, y1 minus y1 cancel out. Bye-bye. Bye-bye. Likewise, in the denominator, our x sub 1's cancel out. Therefore, we just get y sub 3 minus y sub 2 over x sub 3 minus x sub 2 as the slope of dE. And if you notice, they're the same. Y sub 3 minus y sub 2 over x sub 3 minus x sub 2. So algebraically, we just proved that those two segments have to be parallel. And now here is where we get really, really, really fun. It's going to get sloppy. So really, I'm going to try my best to make sure I'm doing it as neat as possible. Let's talk about, to figure out the distance of DE compared to the distance of BC. Well, we want to prove that DE is half BC. So let's try to figure out the distance between them. We are going to be using the same points as before. So B we labeled as x sub 2, y sub 2. C was x sub 3, y sub 3. Therefore, D was x sub 1 plus x sub 2 over 2, y1 plus y2 over 2. Likewise, E was x1 plus x sub 3 over 2, comma, y1 plus y3 over 2. So let's try to figure out the distance of BC. Let's find the distance of BC. So again, the distance, we're going to use the distance formula here. Okay, it's going to be the square root of x sub 3 minus x sub 2 squared plus y sub 3 minus y sub 2 squared. We can technically simplify this here. So we really end up with, ready for this one? X sub 3 squared minus 2 x2 x3 plus x sub 2 squared plus, now again it's going to be the same thing, y sub 3 squared minus 2 y2 y3 plus y2 squared. This is going to be the distance of BC. Whatever those values are of the actual coordinate points, we would be able to take them and plug them in to find the actual distance, right? And this is where we're going to try to compare. So we know that BC, we want to prove that to be double DE. So now that we have the distance of BC, let's try to figure out the distance of DE. So here we go. So the distance of DE, let me try to separate this, because again, it's going to get messy. So the distance again is a square root of the difference of our x's squared plus the difference of our y squared. Well, the difference of our x's, here we go. X sub 1 plus x sub 3 over 2 minus x sub 1 plus x sub 2 over 2. That's squared. Plus difference of our y's, which is y sub 1 plus y sub 3 over 2 minus y sub 1 minus plus y sub 2 over 2 squared. And let me draw my radical. Radical, dude. As you can see, we have some things canceling out. We have these x sub 1's canceling out because it's x sub 1 plus x sub 3 over 2, and then x sub 1, x sub 2 over 2, right? So we will have those common factors, or I'm sorry, we have the common denominators, and we can cancel out our x sub 1's. Likewise, we can cancel out our y sub 1's there. But that might not be effective for us because we're trying to prove that it's going to be half of BC. So let's just keep it and see what happens in the long run. If we were to eliminate, it might not be as easy for us. So let's just see what happens if we keep it. So we're going to end up with, oh no, sorry, I'm doing ahead. Yes, we do want to cancel. So our x sub 1s and y sub 1s, I am so sorry for that, folks. So we're going to rewrite it as x sub 3 minus x sub 2 over 2 squared plus y sub 3 minus y sub 2 over 2 squared. We're going to simplify as best as we can. Let me extend this page. Maybe. Come on, there we go. So we get big ol' square root of x sub 3 minus x sub 2. That eventually turns into x sub 3 squared minus 2 x sub 2 x sub 3 plus x sub 2 squared. All of that over 4 plus, now, again, y sub 3 squared minus 2 y2 y3 plus y sub 2 squared, again, over 4 because we squared the numerator and the denominator. So now we end up with the square root of that. Well, the square root, we can combine these two fractions underneath our radical. So we get x sub 3 squared minus 2x2 x3 plus x2 squared plus now y sub 3 squared minus 2y squared y to the third plus y sub 2 squared all over 4. Now we know that it's going to be the radical of this, or the square root of that, and we can't really take the square root of the top, but we can take the square root of the bottom. The bottom turns into 2. So what we know is that the distance of DE can be written as all of that mumbo jumbo up top divided by 2. But we wanted to prove that it was half as long as the third side. If you notice, and we go back to the third side, well, this is what we have for the third side. The square root of x sub 3 squared minus 2x sub 2 x sub 3 plus x squared, or x sub 2 squared plus y sub 3 squared minus 2 y sub 2 y sub 3 plus y sub 2 squared, right? We have the square root of all that. Well, notice we have everything that we just said again. Except the only difference, let me go back and fill in. The only difference now is that everything is over 2. Therefore, the distance of DE has to be is equal now to the distance of BC over 2, meaning that it's half the distance of BC. Whew, that was fun. That was fun. Thank you for your patience with that as I had to think through this as I was recording. Whew, that was fun. I love proofs. They're so great. Great job with this. If you have any questions, please feel free to reach out. You're doing a great job, and hopefully this answered some of your questions as to how to prove these two theorems.